In the last webcast, we looked at a case where a benzene ring acted as an electrophile in a substitution mechanism and reacted with a variety of nucleophiles. In this webcast, we're going to take a closer look at the nucleophilic aromatic substitution mechanism that's available to certain benzene rings. In our studies of electrophilic aromatic substitution, the benzene ring was the electron-rich substrate and acted as a nucleophile and could react with a variety of electrophiles in halogenation, nitration, sulfonation, and Friedel-Crafts alkylation and acylation reactions. It's important to remember that in those reactions, electron donating groups on the ring facilitated those reactions by making the ring more electron-rich and thus more nucleophilic. However, in nucleophilic aromatic substitution, there's a fundamental reversal of roles of our starting materials. By substituting the ring with strong electron withdrawing groups, such as nitro groups, the aromatic ring becomes less electron-rich and thus more electrophilic at certain positions. With an appropriate leaving group on the ring as well, this electron-poor ring can react with a strong enough nucleophile to substitute for that leaving group. The mechanism by which this takes place is an addition-elimination pathway, and we'll look at it on the next slide. The first step in the nucleophilic aromatic substitution mechanism is nucleophilic attack on the electron-deficient ring at the carbon bearing the leaving group. This nucleophilic addition step creates the resonance stabilized carbanion intermediate prior to elimination of the chlorine. Notice the position of the two nitro groups. They are at the ortho and para positions, and this is important for the reaction to occur. We can understand why it is important to have electron withdrawing groups at these positions, because only then can the negative charge be delocalized through resonance into the nitro group. The second step in the mechanism is beta elimination to expel the chloride anion and produce the 2,4-dinitrophenol product. To sum up the nucleophilic aromatic substitution mechanism that follows an addition-elimination pathway, there needs to be electron withdrawing groups at either the ortho or para positions, or both, for this reaction to proceed at an appreciable rate. Secondly, there must be an appropriate leaving group on the ring. For the reaction to proceed, the leaving group must be a weaker base than the incoming nucleophile to facilitate the beta elimination step. In this webcast, we learned about the nucleophilic aromatic substitution mechanism. This mechanism represents a fundamental change in the way in which we've seen benzene react. In this reaction, the benzene ring is the electrophile and can be attacked by nucleophiles to afford a variety of substituted benzene derivatives.